After transitioning from general chemistry into the foundational material for organic, the first actual class of reaction encountered is usually those between acids and bases. While this topic uses the same ideas and language as general chemistry, the depth of understanding needs to change so that students may use these reactions as a guide to many others throughout the organic chemistry sequence. A discussion of how and why bonds are formed and broken, along with knowledge of pKa values, gives students a platform on which to build. We begin this discussion by reviewing the early ideas of what constitutes an acid and what constitutes a base. The early Bronsted-Lowry definition tells us that acids are proton donors and bases are proton acceptors. For most of the organic sequence, you will notice that acids typically have the proton attached to a more electronegative element, which was the case in general chemistry with acids like hydrochloric, sulfuric, nitric, etc. Many of the acids that you have come across before are also used as reagents in organic chemistry. Hydrochloric, sulfuric, hydrobromic, nitric, and hydroiodic acids are all still exceptionally powerful and will be capable of protonating even weak bases. In each case, the acidic proton is bonded to a more electronegative element, which makes that proton somewhat electron poor. That proton will therefore be able to attract electron-rich bases. Likewise, many of the bases used in general chemistry are also employed in organic reactions. Sodium hydroxide and sodium carbonate are simple examples, and comparing them with specialized bases used in organic chemistry, such as sodium amide and methyl lithium, some common features appear. While the metal ions are usually spectator ions, the associated anions feature an excess of electrons that make them basic. These anions will be inherently attracted to electron-poor protons. Beginning with an example from general chemistry, we know that mixing sodium hydroxide and sulfuric acid leads to water as the conjugate acid and sodium hydrogen sulfate as the conjugate base. In organic chemistry, we are concerned with how and why that happened. It should be obvious that the electron-rich oxygen in hydroxide acts as the base and is attracted to the electron-poor proton on sulfuric acid. If an electron pair from the base is used to attack the acidic proton, then the conjugate base must break off to avoid breaking the octet rule. The arrows used to describe an acid-base reaction are quite simple, since only one bond needs to form and one bond needs to break. We can prove that these events occur at the same time in a concerted manner from the rate equation, which proves to be bimolecular. As we move towards more complicated processes, we must keep track of which bonds need to form and break and match the arrows to the available evidence. As with all of the reactions to be encountered in the organic chemistry sequence, you will need to be able to use the presented clues to work out what is going to happen. Beginning with acid-base chemistry, you should be able to identify straight away which species is the base, which is the acid, and what products are expected to form. Once that is established, we will be able to discuss which side of the equation is more likely to be more stable and therefore favored.